Okay, so that is in Moodle, so just make sure that you check that if you want extra practice in the naming. So things where we were last time. So on Thursday, I don't remember what day it is. So on Thursday, we actually were talking about the shape of molecules. So we kind of introduced this idea. So I added a couple of things to this slide. So one, things to remember. So carbon never has non-bonding electrons. Remember, it's got 4 valence electrons, so it never has non-bonding electrons. So you can identify it according to what they call the ABN designation. And that is just a way of describing a general formula to figure out shape. So it doesn't really matter if you're what the other atoms are that are connected to the carbon. If carbon has 4 single bonds, like what you see in that first one in the example, like for CH4. So if carbon has 4 single bonds, then it would have, for ABN, the A would be the carbon. And so the A is always an A. It's never going to have any other number other than just an A. So it's sort of like how they describe, like to remind you to look at the central atom. B is how many groups are connected to the central atom. So if I look at the first one, carbon was going to have 4 groups. So it wouldn't matter if these 4 groups were all hydrogens or if these 4 groups were all chlorines or fluorines or a combination of them. It's just that carbon, if it has 4 single bonds, then it would have what they call an AB4, because the A is carbon and the B is the groups connected to it, and it's got 4 of them. So they would just call that an AB4. The second one, though, notice that carbon has 3 groups connected to it. So yes, one is a double bond, but that double bond represents 4 electrons that belong between the carbon and the oxygen. So you would say that carbon has 3 groups of bonds connected to it. So this one would be an AB3. So you see the difference between AB4 and AB3. So it's not the number of bonds, it's the bonded groups when you think about what that B actually means. So it doesn't matter if it's a single bond, a double bond, or a triple bond, all of those would count as a single bonded group. Then the bottom one. So the bottom, if carbon has 2 double bonds or a triple bond and a single bond, this is going to be 2 bonded groups. They're going to want to get as far apart from each other as possible, which would put them on opposite sides of the carbon. And this is how you end up with an AB2. So these are 4 very different shapes that you end up with. And like I said, it doesn't really matter what's connected to the carbon. It's just a matter of looking at the central atom, how many groups are connected to it. And another note you can put for yourself is that carbon never has an N. Okay, so notice they call it an ABN. Carbon will never have an N because N are non-bonding pairs. So carbon is never going to have electrons around it that are not part of a bond. So it'll only be AB4, AB3, AB2. Now this is different than what you see like with nitrogen and oxygen if they're in the central spot. So nitrogen, like with NH3, we like to draw NH3 like this, right? So this is kind of where I quit last time. We like to draw it so that it looks kind of like they're one up, one down, one left, one right. So we like to make it look like a little T so that they're evenly spread out. But the thing to remember is nitrogen's different than carbon because nitrogen has these 2 non-bonding electrons. And those non-bonding electrons, they take up their own space around the nitrogen. They are negatively charged because they're electrons, so they will actually repel the electrons that are part of bonding pairs. So all of these are negatively charged electrons. So that 2 non-bonding electron, it is going to push the bonding electrons apart, pushing them so that they cannot spread equally out, like what we saw with AB3, where it kind of makes that little trigonal planar shape. So this ends up pushing those hydrogens down and creates a slight lift to the position of the nitrogen. So they call this the pyramidal shape. So remember that This is the nitrogen, looks like it's a little bit above. It's not flat on the lab bench. What would this ABN designation be? So A would be nitrogen. How many groups connected to it? 3. So this would be a 3 because it's got 3 single bonds. How many non-bonding pairs? 1. So it would just be an N. So because of that N, this is not going to be your trigonal planar. This will end up being pyramidal. And you can put yourself a note. If you see a single N, you know it's a nitrogen, right? Because nitrogen is the one with the single non-bonding pair. So if you see a nitrogen as the central atom, you know there'll be a 1N in it.
Will it always be a pyramidal without an oxygen?
As long as there are 3 single bonds, yes. Okay? And pretty much we haven't talked about anything else, so yes. Because we haven't done like a double bond and a single bond with nitrogen because that's a little different. So we're not going to go there, okay? So if there's a nitrogen, you're pretty sure it's a pyramidal because it's got that non-bonding pair. Compared to when we looked at carbon, so see the trigonal planar? That's a carbon with 3 groups connected, just like that nitrogen has 3 groups connected. Even though one's a double bond, that doesn't matter. It's still just a group connected, but it doesn't have any non-bonding pairs. So these actually spread themselves out. And so you could really say that this arrangement, that this is like 120 degrees, 120 degrees, 120 degrees. You know, a circle is 360. So it's like they're evenly spread. They form like a little triangle. But ammonia or nitrogen can't do that because of those non-bonding pairs. So that creates sort of this, instead of it being flat, it creates this little bit of a lift, which is why they call it a pyramidal shape. Oxygen is the one that has the most non-bonding pairs, so you see the effect even more. So like with water, we like to draw water so that it looks like a hydrogen up and a hydrogen out or a hydrogen up and down. So there's just 2, but they look like they're either on opposite sides or they make like an L. But because of those non-bonding electrons, they're not going to have this like perfect little 90-degree angle because those 2 pairs of non-bonding electrons have an even greater repulsion. So they're going to push the bonding pairs with the oxygen to hydrogens even more than what you see with nitrogen because there's 2 of them. So they create sort of like an even stronger repulsion. And so if you look at, and like you don't have to remember the bond angles, but if they have them listed above, so see how that for nitrogen, the bond angle is 107. For water, the bond angle is down to 104.5. So it's an even smaller bond angle. Just remember that those non-bonding electrons create more repulsion and affect the shape of the molecule as a whole. So they call this for the ABN would be what? If oxygen's A, how many groups connected? 2, so it'd be AB2, and how many non-bonding pairs? 2. So this would be AB2 and 2. So you could put yourself a note, if oxygen has 2 single bonds, it'll always have 2 pairs of non-bonding electrons. So if your geometry ends with N2, you're pretty comfortable saying, yeah, that's oxygen, okay? And it's gonna make this bent shape. So that's why whenever you see molecules of water, they always end up with this bent appearance. The typical drawing of them always kind of gives them this little bent to them, and it's all because of those non-bonding pairs. Okay, so this kind of like summarized, this is a good summary chart where you can see which ones, and I wish they had stuck all the carbons first and then done the nitrogen and oxygen, but they mixed them all in together. So the AB4, good example is CH4, the tetrahedral shape. AB3, good example, CH2O, trigonal planar. Remember, looks like a triangle, but it's flat. AB2, like CO2, oxygens get on opposite sides, so it's going to look linear. Those are the carbons, okay? So those are the ones where you've got carbons are good examples of these. The other 2 examples is where you have nitrogen as an example, and then where you have oxygen as an example. So if nitrogen is in that central atom space, it's always going to have a single N because it's got a non-bonding pair of electrons. If oxygen's the central atom, it's going to have 2 N's because it's got 2 pairs of non-bonding electrons, which creates that bent shape. Okay, so you may want to put like what the ABN number is, what the shape is, and then maybe an example. I'm not going to ask you like bond angles, so you don't have to remember the actual angles of them. So this part doesn't really matter. I'm not going to ask you those. Okay, but an example, and these are the ones that we've actually drawn, right? We've drawn all of these as covalent molecules. So using these as good examples are pretty close to the ones that you're going to see. Okay? So when you see bigger molecules, try to keep in mind that any atom that has more than a single bond is going to have a shape, okay, that they're three-dimensional. So next week in lab, we'll actually do like building organic molecules with the balls and sticks. It'll be the last balls and sticks lab. So you'll get to kind of see how you end up with all these tetrahedrals. Anytime you have carbon with 4 single bonds, it's always going to make that tetrahedral because the electron pairs want to get as far apart from each other as possible. So notice those 2 C's. The 2 carbons in this example, this is ethanol or alcohol. So in this one, the left carbon has 3 hydrogens and then another carbon attached. It doesn't matter what it's attached to. All you're looking for is how many groups does this have connected to it, and that would be 4. The carbon in the middle, you see that it also has 4 groups connected to it. Always the AB4 with carbon, 4 single bonds, always will have the tetrahedral shape. But then looking at that oxygen, and notice how they drew it, because we like to draw things in straight up and down, left and right. We like to put them in a nice straight line. So oxygen, it looks like it's straight, right? It looks kind of like a linear arrangement, but remember those double bonded, the 2 non-bonding pairs are actually going to cause that hydrogen to come off at a bend. So even though this doesn't look bent, just kind of when you see an oxygen with 2 single bonds, just remember, you're always going to end up with this slight bend to it because of the non-bonding pairs. So you'll see this more, and we'll sort of talk about some ball and stick drawings in the next chapter. But just remember that, like, especially when molecules get really big, you'll see how some of the shapes end up being affected. So what's the application to this? Really, the big reason to talk about shape is so that you have this in your mind when we talk about polarity. So covalent molecules, remember this is sharing, right? We're sharing electrons. So if we have 2 atoms that are exactly the same, so for example, if you have 2 hydrogens that make H2, H2, diatomic element, those 2 hydrogens are going to share those electrons exactly equal because they have the same attraction for their electrons. So that means that 50% of the time the electrons end up with the purple hydrogen, 50% of the time they end up with the red hydrogen. So they like go back and forth equally. But not all nonmetals share as well. So this brings up the idea of what they call electronegativity. So electronegativity just refers to atoms that actually hold their electrons and any bonding electrons tightly. So an example I can use, nitrogen, oxygen, fluorine, and chlorine. These are the 4, okay? These are the big 4 electronegative atoms. So if, fluorine is the most, if I drew fluorine compared to carbon, so carbon, I would put its little electrons like this, right? That's pretty much how we've drawn them. If I was really going to draw fluorine and try to depict where its electrons are compared to the size of the fluorine, its electrons would look more like this. So the fluorine like pulls its electrons and holds them really tight. It has electronegative, just means like it is the electron puller, okay? Nitrogen, oxygen, fluorine, and chlorine, those 4 are the big ones. And you can actually look at this chart, which you do not have to memorize. This chart shows you electronegative numbers. These are not on the periodic table. These are just showing you the first 2 columns and the last 6. So notice in these are just showing relative electronegativities. The higher the number, the highest number is 4, lowest number would be 0. The higher the number, the stronger the attraction the atom has for its valence electrons. So first, what do you notice about metals versus nonmetals? Compare the numbers for electronegativity, which have higher electronegativity. Nonmetals. So you see the yellow. So if you look at the yellow elements, you see their number is higher than the purple. Okay, so that really explains why we make ionic bonds, because sodium only has an electronegativity of 0.9. So you could think like it holds its electron way out here. Okay, it just wants something to come by and pull it, because if it can get rid of it, it's more stable as a positive ion. Whereas the nonmetals of like chlorine, nitrogen, oxygen, and fluorine, see how their electronegativity is 3 to 4? The highest of all of them, even higher than other nonmetals. That is why I mark those as kind of like the big 4, because they hold their electrons tighter than any other nonmetal, than any other metal.
When you said the numbers are bigger, are you talking about like...
See the number underneath the symbol? Okay, so that number is, it's really kind of like a number they decided on. And you don't have to memorize them, because the periodic table actually shows you. That number tells you how tightly do these atoms hold their electrons. Okay, and so anything 3 to 4 is really high. Anything 3 to 4 is pulling in really tight. Anything that's less than about 1.5 is sort of like, here, take it. Okay, trying to give its electron away at any possible chance, and that's typical for metals. Sodium, potassium, calcium, electronegativity increases as you go from left to right, because remember, as you go from left to right on the periodic table, the number of valence electrons increases by 1 each row, right? So as we go from carbon to nitrogen to oxygen to fluorine, there's 1 more valence electron. It's getting closer and closer to 8. It also increases as you go bottom to top. Smaller atoms have their valence electrons closer to the nucleus, right? So nitrogen, oxygen, and fluorine, they've really, all their valence electrons are in the 2nd energy level. So that's pretty close to the nucleus, which is why they have a stronger attraction. You can think like the little positive protons in the nucleus are closer to those valence electrons, so there's a stronger attraction. So above all else, the big ones to remember are NO, F, and CO, okay? And you just have to remember it on the periodic table, okay? Nitrogen, oxygen, fluorine, chlorine's right underneath. The ones that are in that upper right-hand corner, those are the strong ones. So I gave you the examples like hydrogen, 50-50, okay? So I also, like when we were talking about sharing electrons, I gave you the sort of like the shared custody type of thing. So like H2, that would be like equally shared custody. The electrons spend 50-50, okay? Spend 1 week with one parent, 1 week with the other parent kind of thing. I don't know how people do that, but that's like sometimes that is a child rearing effort that both parents make. Even if I have O2 though, so notice O2, the next one down, even though oxygen is electronegative, if I have 2 oxygens, they can't pull electrons more from one another. So they also would end up sharing equally. They would also have a 50-50% because they have the same attraction, even though they're both electronegative. But then look at HCl up above. So HCl, if I have that purple hydrogen and the green chlorine, chlorine pulls its electrons close to it. The hydrogen then only ends up with its electron about 20% of the time. 80% of the time, the shared pair are around the chlorine. So that means that there's more electrons around the chlorine than around the hydrogen, and that makes that chlorine slightly negative. It doesn't make it a charge. It's not an ion, right? Because these are covalent bonds, but because they're not shared equally, it causes those to get pulled, the electrons get pulled towards the electronegative atom, and that creates a slight negative. That's what this strange looking symbol, it's supposed to be a delta. Mine ends up looking like a strange figure 8, okay? Like an open-ended 8 is sort of the look to it, but it just means slightly negative. So over on the opposite side where the hydrogen is, because its electron is over with the chlorine 80% of the time, this hydrogen, which is usually 1 proton and 1 electron, is now kind of like a little proton, which is positively charged. That's why this becomes slightly positive. That's what that little 8 with the plus is indicating. It's not making an actual ion, so we're not talking about metals and nonmetals. This is with all nonmetals and hydrogen. If you have 1 nitrogen, oxygen, fluorine, or chlorine in a molecule, then you are safe to say, as a rule of thumb, molecules that are small, so we're talking like less than 8 atoms, okay? So if you have atoms 4, 5, 6 atoms, this holds true. If you see a formula and there is only 1 nitrogen, oxygen, fluorine, or chlorine, then you can say they do not share their electrons equally. They are polar. That is what a polar molecule is, okay? All it means is that we end up with this unequal sharing of the electrons, creating a slight positive and negativeness, and that creates a polar molecule. So if there's none, if you look at a molecule like CH4 down at the bottom in the left, CH4, you look at it, look at the formula for CH4, there's no nitrogen, oxygen, fluorine, or chlorine, then you go, oh, they share their covalent bonds equally. This is a chemically neutral or a no charge nature to it. This is a nonpolar molecule. So nonpolar molecules have no slight charge nature. They are very neutral. I think of polar molecules, they're like pieces of plastic, okay? So if you have pieces of plastic, do they have any attraction at all? No. You throw them down, they just go on their way, right? So there's no slight attraction to them. That's a nonpolar molecule. So if there's no NO, F, or Cl, then you know it's going to be nonpolar. If there's more than 1 NO, F, or Cl, that's where you have to look at shape. Because shape, which we just finished talking about, does come into play. So the one on the far right, carbon dioxide, CO2, is an example for this. So when you see the formula of CO2, you go, oh, there's oxygen. And you want to go, oh, that must be polar. But there's 2 of them. So then in your head, you have to think, okay, carbon dioxide, what does it look like? So you got to remember the carbon's in the middle. The double bonded oxygens form a linear shape. They want to get on opposite sides. So because it has that linear shape, can you see how this example on the right, how those oxygens balance each other? So yes, they both pull electrons, but they balance because they're on opposite sides. Because of that, balanced electronegatives are also nonpolar. You can think of them, they like cancel each other out. And so the molecule as a whole ends up being neutral like the plastic. Okay, so those are sort of like the 3 conditions. When you talk about atoms that are bigger than 8, so when we start talking about like sugars, lipids, proteins, when you start talking about big molecules, then it's really how many nitrogens and oxygen. If you got lots of nitrogens or oxygens, then yeah, it's going to be polar. But if you only got a couple, then and lots of just carbons and hydrogen, then it's probably nonpolar. So we'll look at those, just kind of try and keep those in mind as we go along through. So there's the kind of example, and I can try to zoom it. I had no luck last night. Zooming was not acting normal. See? Okay, so you kind of saw it for a minute before it went away. So you can see kind of the H2. They put those 2 red dots like exactly in between. That's a nonpolar molecule. There's no nitrogen, oxygen, fluorine, or chlorine. The electrons are exactly between the 2. They're shared evenly. But then the example over on the right side, HCl, can you see that the red and the black dots are like over on the right? That they're like pulled over to the chlorine. So that means that side, this is the side becomes slightly negative. Here's how they do it. This is what mine ends up looking like, kind of like that, okay? So kind of like a weird figure 8. I kind of like don't make the top that means this is slightly negative. This side becomes slightly positive. And I'm like, that's that symbol, slightly. So that symbol, it's the lowercase Greek delta symbol, and the term means slightly. So it's not an 8. It just kind of looks like this. Okay, question?
So the one with the most, like lone pairs.
The ones to remember, NOFCl. Okay, if you see NOF or Cl, so that's chlorine. I know it's hard to see. When I see this, don't worry about like the number of lone pairs because bromine's got a whole bunch, but bromine's not very electronegative because it's so big. Its valence electrons are really far from the nucleus, and so it has less of this effect. Just remember NOFCl. If there's only one and it's less than 8 atoms, polar, move on. Okay? Just look at a formula. If you only see one NOF or Cl in the formula, then you know it's going to be polar. There's no examples where it's not.
Are we gonna have to do anything with the figure 8 thing?
Like labeling them? No.
Okay.
Okay? But it is a delta symbol. Their way of drawing it looks kind of like that. The way that you will always see me try to attempt to draw it, it looks sort of like that. Okay? It's just supposed to, and it's what the whole reason, it would be nice if they would just put SL, slightly. I like SL negative, but no, they got to stick with these like strange symbols, and again, I don't always get to make the rules. All right? So if it's equally shared, right, so the electronegative, if they're the same atoms or if there's no NOF or Cl, then see how those bonds look like they're kind of the same, the green? So they're evenly shared, that's nonpolar. That's chemically neutral, like plastic. So they just form their individual molecules, and they don't really have much attraction. If there's an unequal sharing, then we end up with the polar molecule. Remember, that's just one NOF or Cl. In the extreme, when we talk about a salt, like NaCl, they transfer electrons. So they are ionic. Okay, so in terms of the strength of this bonding, ionic has such a strong attraction, there's actually a transfer of electrons, whereas covalent, we have sharing, but we don't always have equal sharing is the key. So what is this application, and how is this sort of interesting to think about? So one, polar molecules versus nonpolar molecules. So when you think about covalent molecules, remember these are not salts, covalent molecules that share their electrons. The most polar molecule is water because it's really small and it has oxygen, which is very electronegative. And so when water molecules, that oxygen always becomes slightly negative. The hydrogens then become slightly positive. And if they come in contact with any other polar molecules, the slightly negative parts are going to be attracted to the slightly what? Positive parts, right? Because opposites attract. So polar molecules like water, they like to group together. And the negative, slightly negative parts connect with the slightly positive, and that allows them to get closer together. So I have two of them drawn here. I have nitrogen and ammonia, so H2O and NH3. And so notice in this, do you see how this slightly positive and slightly negative, that arrangement, the hydrogens of the water want to get close to the nitrogen of the ammonia because the slightly positive is attracted to the slightly negative. This is why you can take ammonia and water and mix them. You can take and mix them, diluting the ammonia, and it stays mixed because they have the same polarity. Same thing, if you've ever mixed, like last weekend, I had to clean the coffee maker. So it starts after a while, you're like, tastes kind of funny, and it's brewing really slow. So you run a couple rounds of vinegar through, right? So you pour vinegar in. Vinegar itself is only about a 35% solution. So that means 35% is actual vinegar molecules, 65% is water molecules. So it's a solution. You pour it in, you let it run partially, you shut it off, let it sit. The acid in the vinegar helps to dissolve the sediment from the coffee and all the brewing. Then you turn it back on, let it run through. Are you done? What do you got to do? Yeah, you got to run it back through water like 5 times, or else what you're going to drink next time, you're like, it still tastes like vinegar. Okay, so like I'm like, like every once in a while I run another pot, smell, until I don't smell any more vinegar, because I really don't want vinegar tasting coffee. But water and vinegar, because they mix and they stay mixed, they have to be polar. Okay? Things that mix with water have to be polar because they create this slight charge. So water, ammonia, vinegar, some solids as well, like sugar. Sugar has lots of oxygens. It is 6 carbons in size, so it's kind of big. It's got those 12 hydrogens, 6 oxygens, but it's got lots of oxygen scattered about, so it's also polar. So when you take sugar, put it in water or put it in your coffee and stir it up, it's going to be polar. All the pigments that filter out of your coffee grounds, they're also polar, okay? Because they mix with water. So that's like the best rule of thumb. If it mixes with water and it's a covalent molecule, it's got to be polar because they mix and they stay mixed. Salts are another example, though, and the reason why water is such a great solvent is because water is polar and salts are charged. They're ionic. So when I mix ionic salts with polar water, it gives the salts the ability to dissociate or break apart in the water. So remember, if you take table salt and you put it in water, what ends up happening? What do you end up with? Na charged aqueous, right? So I end up then, the sodium and the chloride ions don't stay together. They can actually separate and free float in the water. All right, so remember we talked about electrolytes. So we talked about the importance of sodium and potassium, iron, chloride, magnesium. There was like a whole list of them, the different ones, but both of these now are ionic. So now, in fact, in your blood, sodium ions don't float connected to chlorine. Sodium ions free float. So sodium ions and chloride ions are sort of floating around in the solution of the blood. So polar molecules mix with polar molecules. Polar molecules can mix and dissolve many salts. But that then leaves these. So the nonpolar, remember, either have no nitrogen, oxygen, fluorine, or chlorine, or they have a balanced arrangement of them. These have an equal distribution, so I said they're kind of like plastic. And so if you put a piece of plastic in water, what does it do? Just floats along. No, AQ, that's an L, because water's a liquid. Remember, those are like the species. NaCl as a solid plus H2O as a liquid would make Na plus aqueous and Cl minus aqueous. Those are just sort of their states. Remember, aqueous just means it's dissolved. But in the nonpolar, so if I have something like CH4, no carbon, no hydrogen, no nitrogen, oxygen, fluorine, or chlorine. If I have Cl2, which are 2 chlorines, but they're side by side, so they would balance themselves, just like O2. CO2, another example. You could have C6H14, which is hexane. You could have really big groups of carbons and hydrogen. If they have no nitrogen, oxygen, fluorine, or chlorine, then they're all sharing their bonds equally. They're nonpolar molecules. Common examples, gasoline, all of your heating fuels, so like kerosene, gasoline, diesel fuel, motor oil, all your cooking oils, so think about like olive oil, vegetable oil, canola oil, butter, lard, shortening. How do all of these feel? When you get these on your hands, they are greasy, right? All of your greasy stuff, all of those are nonpolar. So what do you know happens if you take oil and you mix it with water? They're going to separate out, right? So what about like your vinegar and oil. How does it look in the dressing bottle? It's separated, right? The oil's up top and then the vinegar and spices are at the bottom. And you shake them up and you pour it really fast before it separates again, or else you just end up with a big glob of oil. It's really gross. Okay? So, you know then, these ones on the opposite side of the red line, they don't mix. Polar and nonpolar don't mix. In terms of the body, we'll talk about lipids. Lipids are a nutrient group. So your big nutrient groups are your carbohydrates, right? The sugars and starches, proteins, your meats, and then lipids. Lipids are your fats and oils. Lipids have big importance. Lipids really are good at making barriers because things that are polar and things that are ionic cannot dissolve in it. So the next time you have to fry something, just as an interesting test, or if you have to just put a little bit of oil in the pan before you cook something, just shake some salt in and watch. Does the salt dissolve? If you have a little bit of oil in your pan and you shake some salt in, does the salt dissolve? Why? Because salt is charged, right? Salt is ionic. Lipids, nonpolar. So you will see that little crystal of salt will just drop right to the bottom and you're like, you can take and mix it. Doesn't go anywhere, okay? Polar and nonpolar don't mix. Nonpolar and ionic don't mix. They're gonna separate out. So we actually have to do some special things to try and absorb them. But we will talk about these in the next chapter. We'll introduce lipids as the big nutrient group. So remember that this includes all of your fats and oils. They have importance, but you've got this challenge of a polar, nonpolar. Your blood is polar. So how do you manage to transport fats about, right? Without them separating and ending up forming a little layer like your salad dressing bottle. So we'll talk about that more. Okay, so now, last topic in chapter 3. See if I can get it to come back right. So the last topic in chapter 3 is counting. This is the only math. So if you didn't grab a calculator and you don't have a calculator, you need to really get a calculator. Okay? So if you have your calculator that you're going to use on your exam next week, make sure that you get it out. So this is, like I said, this is the last math, and one of the big things with this is making sure that you know how to put this in your calculator, because that's really why people get this wrong, okay? So chemists wanted to be able to measure amounts of ionic and covalent molecules, being able to actually have a measurable amount, because when you talk about, the periodic table, you're talking about atoms, and when you're talking about atoms, they're so small, there's no way you could physically see, much less measure out a single atom. So you're like, well, how do we scale up? How do we scale up numbers of atoms to a measurable number of atoms that's consistent despite the fact that every atom has a different mass, right? So hydrogen has a mass of 1, carbon has a mass of 12. So how do we count the same number of atoms and then also take into account the number of, or the amount, the atomic mass of each one of those? So they came up with this. It's the mole. The only thing I can say is maybe because it's short for molecule, maybe that's how the mole came up. I don't know. Okay? So it's sort of like a historical thing. So the mole, they just use it as a counting number. Right? And so their example, I like their example, the dozen. Now, why they didn't decide 10 was a good counting unit in Old English times, I don't know, because 10, 20, 30, 40. Instead, you got to go 12, 24, 36, 48, right? You got to multiply everything according to 12. But in the Old English, the dozen was the norm. And then you have the baker's dozen, which is an extra. That's 13. Not sure how that even came about. But maybe it was the number of eggs that could comfortably fit in a bowl or something like that. There must have been a reason that 12 became this number. So we're going to use the mole. So the mole counts for 2 things. So they measured based on the atomic mass. 1 mole of anything is equal to its gram formula mass. This means it is the mass of any molecule expressed in grams. That's what they call the gram formula mass. So if I have 1 mole of carbon atoms, how much would it weigh? So how do I figure this out? Look at your periodic table. What is the atomic mass of carbon? Everybody see 12.01? That is always the number with the decimal place, the number under the symbol. So that's its atomic mass. Just round that to a whole number, and that's how I figure out its formula mass. So we just have 1, because it's just the mass, 1 mole of C. So it's just a single one. So then what if I have 1 mole of water molecules? How much would that weigh? In grams. So to find that, the gram formula mass, you just take the mass of each atom in the formula. So the formula says I have how many hydrogens? 2 hydrogens, and each one weighs 1.008, just round to a whole number. So that would be, so each hydrogen would weigh 1 gram. That means that that's 2 grams. Then I have 1 oxygen. What would its mass be? 16 grams in a mole. And so that would be 16. Now you just add them up. It's just the mass of each of the atoms in the formula expressed in grams. All you need is a periodic table and a calculator. Okay? You don't have to like figure anything out. You're just looking at the periodic table. 2 hydrogens, each one weighs 1, so that's 2 grams. 1 oxygen, which weighs 16 grams, add them together. Okay, let's run another one. What if I have 1 mole of H2SO4? How many grams is that? Okay, so from the formula, how many hydrogens? 2. I have 2 H's. How many sulfurs? 1. How many oxygens? 4. How much does each hydrogen weigh? 1. Look on your periodic table. Number underneath the symbol 1.008, round it to a whole number. So that's going to be times 1. Sulfur, how much does sulfur weigh? 32 grams. How much does each oxygen weigh? 16. Does everybody see where I'm getting those numbers? If you don't have a periodic table, you need to come and get one so you have one like right in front of your face to look at, because going like that like kind of slows you down doing the big squint trying to see all the way across. Okay, there's a big stack over here. Don't be shy. Come and pick one up. So all you do is you're just multiplying the number of atoms times the atomic mass and then adding them all up. So 2 times 1 is 2. 1 times 32 is 4 times 16 is 64. When I add all those up, you get 98. It's not any harder than that. Okay, they call it the gram formula mass. So you got it now?
I think so.
Okay, so you just look at the formula, like don't make it any harder. Just look at the formula and use the periodic table. Whatever the formula is, you multiply the number of atoms in the formula times its mass. You do that for hydrogen, for sulfur, for oxygen, and then you just add them up. Yes. So the formula tells you how many of each. The periodic table tells you the mass of each atom. Okay, shall we do another one then? So 1 mole of glucose. One mole of C6H12O6. Tell me what its formula mass is. This is the number of grams in 1 mole, right? So they're equal. So see, I can use this as a unit conversion. So it's just like saying grams to milligrams. This is just moles to grams. As long as I can find the formula mass, I can figure out the number of grams in any number. I could figure out 2 moles, 5 moles, 0.683 moles, 100 moles, any number I could use. I have to find this first, okay? First, just do this. Okay, so find the number in 1. So C6H12O6, let me change colors so you can see it. How many carbons? 6 carbons. How much does each weigh? 12. So that is 72. Hydrogens, how many? 12. How much does each weigh? So that's 12. And then oxygen I have. And each one weighs, so how many is that? 96. Now add those up. So you have to add 72 plus 12, 84, plus 96, 180. Did anybody not get that? There's 180 grams in 1 mole. Everybody got that? So, how many grams would be in 2 moles? What would you do? Multiply it by 2. That's it. Okay? Right? So if that's the number in 1 mole, then if I wanted to know the number in 2 moles, I would just end up doubling this number. Right? So if I had 4 moles of water, how many grams? I think of this as a unit conversion, but this is a single-step unit conversion. I can do this in 1 step. If you see moles and grams or grams and moles in your problem, you can solve this answer in 1 step. If you see moles and grams, or if you see grams and moles, you can do this in 1 step. You just need to know the formula mass. I need to know how many grams in 1 mole. So we did water already. So we said H2O has 18 grams in 1 mole. Right? So I said 18 grams equals 1 mole. Well, that means I can have 18 grams over 1 mole, or I could have 1 mole over 18 grams. It's saying the same thing, just like 12 eggs in 1 dozen, or 1 dozen in 12 eggs. Right? You can flip it, use it like a unit conversion. You can do this, it's really like a single-step unit conversion. So what am I given? 4 moles H2O times in a line. What unit will I put on the bottom? Moles, okay? Moles will go on the bottom. Whatever you're given will always go on the bottom in this step, okay? It's a way to make sure that you do the right multiplying or dividing. So I know I got to put moles on the bottom. The answer I want is grams, okay? So this, if you set it up this way, whatever you're given goes, the unit goes on the bottom, and the answer you want goes on the top. That's, I don't randomly put them there. I put them there because you want moles and moles to cancel, right? So like when you do math, if you have the same unit in the numerator and denominator, they'll cancel. Now I just take those numbers from the gram formula mass. So in front of grams, I put 18, and in front of moles, I put 1. Right? So I just used this like a unit conversion, but it's only 1 step. I don't have to do more than 1 step, and we're not going to do any that need more than 1 step. Unlike Chem 151. 4 times 18, 72. All I do is take 4 times 18. Okay, so what if I had 125 grams of water? Can you do that in your head and tell me how many moles this is? So this is where, like, setting it up will always make sure you multiply and divide correctly, okay? If you do it in your head, okay, but there will be times when you're like, I don't want you to divide when you should multiply. And if you set it up this way, you will always set it up and multiply correctly or divide correctly. Does everybody understand up there? I'm taking 4 times 18 divided by 1. Everybody sees that in that math calculation above? That is why it ends up being 72. 4 times 18, everything, you can kind of think like this is everything across the top, okay? 4 times 18, then divide by 1, which doesn't change anything. So that's 72. But if I had 125 grams of water, how many moles is that? I already know 18 grams in 1 mole, so I can solve this. 125 grams times in a line. What goes on the bottom now? grams, okay? Whatever unit you start with, that's what goes on the bottom, and that tells me moles goes on top. Now, what goes in front of moles? 1, right? So I'm using the gram formula mass. Moles will always get the 1. And then how many grams? 18. So now do this math. So if you take 125, I can't do this in my head. 125 and divide it by 18. 6.944444444 moles. Right? 10 digits total. Yep, I got 10. Because that's the most. It would just be 444. Keep going. Okay, so what do we have to apply? Eek. Now I go back to chapter 1 stuff. Okay, look at the top number, 4 moles of water. How many significant figures in 4? 1. So, can I keep 72? How many significant figures in 72? 2. I have to round that so there's only 1 significant figure. So, the 7 stays. What happens to the 2? Becomes a 0. Right? So that, with correct significant figures, would be a 70. Remember, a 0 at the end is not significant unless there's a decimal place. So 70, and really what that's saying is it's keeping the same amount of exactness in the number as the number in the problem. If I have 1 significant figure in my measurement, then I have 1 significant figure in my answer. The 18, you figured out using in the periodic table, right? That's not a measured number. This is the number off of a chart. So that is why 18 doesn't matter in the rounding. Always look at your measured number. So it's always like the number in the problem. Anything you use the periodic table to figure out doesn't count. Kind of like when we did grams to milligrams. Like remember unit conversions, you don't use those numbers in figuring out rounding. Always go back to the measured number you start with.
So if it's like 4 moles, that one has 1 significant figure, so we make it 70 because it's 1.
Correct, because 72 is 2 significant figures. That's 2 exact. Same thing down here. How many significant figures in 125? 3. So that means my answer can only have 3. So what would my answer be? 6.94. I keep the 6, the 9, the 4, but all those others drop off. I keep the decimal place because it shows where the size of the number is. So that decimal place still stays, but I keep the 6, the 9, the 4, the rest of them drop off.
So how did you change the one on the bottom? Like how did you do the one on the bottom?
For this one down here, okay, so look in the way that I set it up. So 125 grams times in a line. What unit goes on the bottom? Grams. What unit goes on top? The one I want, moles, right? So my given unit goes on the bottom, my answer goes on the top, because this is a single step. It's not going to be any harder than that. I don't have to do any more times in the lines or anything like that. It's one step. So I know, based up here, water has 18 grams in 1 mole. So mole always gets the 1. Okay? So mole will always get the 1, and the grams is the mass based on the formula.
So
That's why it's moles per 18 grams. I just flipped that unit conversion so that grams and grams cancel.
so that's when you divide it.
Correct. So now this means 125 times 1 divided by 18. So you can kind of think like it's this, right? Everything across the top is multiplied. Anything in the bottom is divided. Okay? So then the next question became, well, how many particles are these? Okay? How much is this? When we're talking about 18 grams in 1 mole of water, how many molecules of water is this? So Avogadro, he worked on this like his whole life. Okay? And in fact, they ended up naming this number after him. This physicist, so yeah, there are not just all chemists. So physicists did this. So he was like, okay, so knowing how much water weighs, knowing how much hydrogen weighs, knowing how much carbon weighs, he did like all these calculations based on the size of atoms and how close they are together to try and figure out well, how many actual particles is in this 18 grams of water or 12 grams of carbon. And he found there's a lot. There is 6.02 times 10 to the 23rd particles, this could be atoms or molecules, in any substance. So 1 mole of anything is 6.02 times 10 to the 23rd particles. So this, you don't even have to calculate. This is like a given, okay? So I know that if I have 1 mole of water, to figure out the number of molecules, I know that 1 mole of anything has 6.02 times 10 to the 23rd molecules. So in this is again, it's just a single unit conversion. I just put what I'm given times in a line. The unit I'm given goes on the bottom. The unit I want to find is going to go on the top. And in fact, so this was done like 400 years ago, 350 years ago. This is not something that somebody figured out this in the last 100 years. So he had his little abacus, his little beads. He was like doing all these crazy calculations. And he was like, he's really close, okay? Really like, so it was pretty astounding that someone could like work this out. You know, he was a physicist. He probably lived at home with his mom, all right? But that was like the super curious, like how close these atoms are, their size for any mole of any substance, whether you're talking about like carbon atoms, or if we're talking about water molecules or sugar molecules, any kind of substance, there are 6.02 times 10 to the 23rd molecules in 1 mole.
So we don't have to do all that stuff that we
No, you don't have to do any other calculations, you just have to remember this. Okay, so if I know, so what if I have 15.3 moles? And this one, you really do want to make sure you set it up, because I don't think you can do this one in your head. Okay, if I want to know how many molecules. How do I solve this? What do I put down first? Okay, and we'll just say water, because I didn't specify what it was, but it could be anything. It doesn't really matter. And it moles, 15.3 moles of anything. So I put down what I'm given first, times in a line, what goes on the bottom, moles, right? Whatever you're given goes on the bottom first. What goes on top? Molecules, which is my answer. So notice when you're looking at this, the given unit will go on the bottom all the time. Your answer goes on top. So now you just have to make sure you put the right number on the right line. So molecules gets what? And moles always gets the 1. Right, so just like in the last one, we had grams per mole, mole got the 1. In this one, molecules per mole, mole still gets the 1. So now I have to do this math. So if you have your calculator, there is a special button on a calculator for this that I really like. And it's called the EE button. So if you have an old calculator, if you have a graphing calculator, you just gotta find it. Find the capital E button. Okay, if you have a graphing calculator. Sometimes you have to hit a second button. You see it? All right, so that EE, capital E, this is times 10 to the. So here's how we're gonna put this one in. So put 15.3, right? Times, because I'm multiplying everything across the top, times 6.02. Now I want you to hit that EE button. For people with the old school calculators, do you see like 2 little zeros show up in the upper right corner when you hit the EE button? If you have an old school calculator, if you have the graphing calculator, yours will now have an E. Do you see an E after? Same thing, okay? If you have my calculators, do you see those little zeros? Now put in 2, 3. Do you see that the 2, 3 go into after, if you've got a graphing calculator, the 2, 3 comes after the E. If you have mine, do you see the 2, 3 show up in little numbers in like the upper corner? This means 6.02 times 10 to the 23rd with parentheses. Parentheses are automatically added if you use the EE, which is wonderful because if you've used a graphing calculator, you know how you have to add parentheses. You don't have to if you use that button. And I don't know why math teachers don't use it. Now hit equals. What do you see as your answer? 9.2106. And then you have this, or you have 9.2106E24. Do you have that? Okay. The top one is the old calculator, so you just see that. This means 9.2106 times 10 to the 24. That's what that means, okay? So just put yourself a note what it means when you see those little exponents on the old calculators up. That means it's times 10 to the, and whatever those little two numbers are. If they're negative, they'll show up as a little negative up there. If you have a graphing calculator, yours looks like this. So that's the fancy graphing calculators. Just remember, you got to convert it back. Did anybody not get that number? Okay. Okay. So if you put, so did you do 1.53 or 15.3 times 6.02? Do you see an EE?
I don't have one.
I've not seen one yet that doesn't have it. Yours you have to do, like when you do, when you put in exponents, do you do like 10 times and then do the little caret up? So you'll have to do the caret up 23. Or no, it's this. That's the same as EE. Sorry. I knew that was the same. So see where it says times 10 to the x? Yep. So try to put that in. Clear it. 15.3. I just want to see if that's right. 50 times. So x. 102. Now, that 23. Straight back. I was like, I've never seen one. See right there?
No, I did that,
Yeah.
but I'm trying to enter it into.
No, not E first, just 15.3 times 6.02 EE 23. So you put the EE where the times 10 to the, huh?
I put the E first, that's why mine didn't come out right.
Oh, yeah, okay, so if you were putting this in, so I would say 15.3 times 6.02, then I would hit the EE button and then the 23, not 24, Holly, come on, 23. Like, that's the order that I would put it in, okay? I would actually put it in my calculator that way. 15.3 times 6.02 EE 23. And what this does though is it puts those, it actually makes this parentheses around the 6.02 times 10 to the 23rd, because if you've ever done exponents and you don't remember to put the parentheses, it'll multiply 6.02 and separate it from the times 10 to the 23rd. Everybody got that? Okay, so what about significant figures? Because we can't leave that out. How many? 3. Okay, so with your answer, starting for the left, what's the first 3 significant figures? 9.21, right? So what happens to the 0.6? That drops off. So I would have 9.21 times 10 to the 24th molecules. So you don't drop off the exponents, you just round out your number in front of the exponent.
That answer to the 23rd degree.
Did you get 92.1? 9.21. All right, I'll have to look at it at one then with the next one. No, because again, that's Avogadro's number. So that's considered kind of like speed of light, Planck's constant. That's considered a constant. So remember when you go, always just look at the number in the problem. Okay, so you won't take significant figures from Avogadro's number or a gram formula mass. You'll always just take the number from the problem. All right, so let's do a couple. So there. 1, 2, 3.
I have another question too.
Okay, so see if you can answer those ones. just because you put 1.5.
Okay, I had to go
You gotta hit clear, don't turn it on.
Okay, I'm sorry, that's just, and then I realized I didn't turn it on. The molecules we use the big old smoke numbers, and then for the grams we use like that. Okay, that's what I was confused about, I didn't know, I thought it was that way, I was just like, then why don't we do all these if we use the other?
These are just the two things you can do with moles.
Okay, that's why I was like, I said, why you're not this, use this, but it's because I have to do numbers for that.
Yeah, if you do moles and grams, or grams and moles,
I see what you're talking about.
then you know you need to do formula mass. Where you
Okay.
gotta
But
figure
the
out the
last
number
one
of
you have to
mass
use
in
the-
one mole.
Okay.
If you see moles and molecules, or molecules
Oh,
and
it's
moles,
only from
then you're gonna use
Oh.
mass.
Okay,
Okay?
okay.
So it's sort of like the mole counts as two things, it's the mass, but it also counts for number of particles,
Okay.
okay? Right, because remember mole always gets the one, so like looking here. Right, so 6.02 is the number of particles, atoms, molecules, particles, whatever, mole always gets the one. Okay, and it's the same thing here too, so see it's 18 grams per mole, so mole will always get the one, but that is kind of like a side note. Whenever you're doing this, moles is always the one, grams is the formula mass, molecules or atoms would be Avogadro. Right? Because what it's not doing is it's not wanting to put parentheses. Why did it work for me? What did you do? Oh, no, yeah. Oh, that's because, so I call it that because that's what that is. So see how it's EE? So you only have to hit it once. I was like, okay. No, I mean, that's the thing, is like, if you've never used the EE button, you're like, what?
Why don't math teachers use that? That is so
They-
much easier.
Well, and it takes out a lot of the exponent issues. Like if you have to divide two big exponent numbers and use EE, like if I have to divide 1.6 times 10 to the minus 30 divided by 1.5 times 10 to the minus 29, and you use EE, it puts the parentheses around them automatically, which is nice. But instead of you having to remember to go back and do like parentheses this, parentheses that before you do the math, because that always used to make me like scream. And then I found this and I was like, what is this number? What is this formula? How does this work? All right. Okay, so here, for the first one, I give you the gram formula mass. So it's H2SO4. We actually figured this out in a previous one. So 2 hydrogens, each weigh 2. 1 sulfur weighs 32. 4 oxygens weigh 64 total. Add them up, it's 98. Right, so you did that on a previous one. So all I would do is take 1.5 moles times in a line. What unit goes on the bottom? Moles. Right? Whatever unit you start with goes on the bottom, and the answer you want goes on top. So this just tells you where to put the 98 and where to put the 1. So grams gets the 98, moles gets the 1. So in doing the math, what did you end up with? 147. Okay, going back, change color. How many significant figures in 1.5? 2. So that means I'm going to keep the 1 and the 4. The next number is a 7. So what does that round my number to? 150. Okay, so remember I still keep that 0 at the end because I'm rounding 147 to 150, not 15. You don't want to take $147 and round that to $15. You would like to round up. If you're doing your taxes, I would like to round up or round down and keep the same number. So same thing with this one. It's using the same one. So 50 grams times in a line. What unit goes on the bottom? Grams. right? The unit that I'm given goes on the bottom. The unit I want to find goes on top. Moles gets the 1, always. Grams gets the 98, right? So put yourself a note. When you're doing these, moles gets the 1. Moles always gets the 1, whether you're using Avogadro's number or the gram formula mass. So now I take 50 and I divide it by 98. And I got 0.510204082 moles. Can I keep all that? No, right? 50 has how many significant figures? 1. So I know that that's like, that when you look at a number, you're like, oh, I'll just keep, like the random thing is just to keep what looks good, but just go back to your number and check. So if it's 50, there's only 1 significant figure in 50 because the 0 has no decimal place. So that means it's this. So I'm going to keep the 0.5. 0 out front's not a significant figure, but I got to keep it because of the decimal. The next number's a 1, so all of that does what? Drops off. So it's just 0.5. Okay? So here's this one I want you to do. 1.3 times 10 to the 21st molecules of CH4 is how many moles? And this, I think, shows you really why the EE button is so helpful. So I don't have to do any other, I don't have to know the formula mass. All I have to remember is Avogadro's number. So you're probably going to want to put that on your sheet. 1.31 times 10 to the 21st CH4. Well, molecules. Times in a line. What unit goes on the bottom? Molecules. The unit you're given goes on the bottom. And what goes on top? Moles. The unit I want. My answer. Right? So notice what I start with always goes on the bottom. My answer is going to go on the top. It's just a single step. What goes in front of moles? Moles always gets a 1. What goes in front of molecules? Times 10 to the 23rd. So now I want you to put this in your calculator. 1.3 EE 21. So it should be like 1.3 and then a little 21 divided by 6.02 EE 23. I got 0.002159468. So I put 1.3, then my EE, 21, and then divided it, because see how 6.02 times 10 to the 23rd is in the denominator? So then I divide it by 6.02 EE 23. Don't have to use parentheses. They go on automatically, and then hit equals. Did you get that? Okay. 0.002159468. Everybody got that? All right, how many significant figures in my answer? It needs to have only 2, right? Because there's 2. Ooh, there's 2. I love this. God, stop. There needs to be only 2, so that would round to what? Still trying to do it. There, 2. So going along. The 2 and the 1 are the first significant figures. Remember, 0's out front. I keep them, but they're not significant figures. So that 1 becomes a 2 because the next number is a 5. So this would be 0.0022 moles. Okay, so you can practice those other ones. We'll run through them first thing, then we're going to go on into chapter 4 next time. For anybody that came in a little bit late, I was telling the other class, I had a student in another class that said, hey, can I have some more naming practice questions? So I was like, sure. So in Moodle, for exam 2 module, there's now a Chem 130 naming practice chapter 3, and then the answers is underneath, okay? And there's like 17, 18 of them, identifying them as ionic or covalent, and then naming or giving formulas just for practice. So those are posted there for you if you want to do them.